Right now, a quiet crisis is unfolding inside the world's most advanced data centers. We were promised artificial intelligence with infinite memory. Tech giants bragged about context windows holding millions of words, suggesting AI could read entire libraries in seconds. But it was an illusion. In reality, the systems keeping track of those millions of words are hitting a physical wall, consuming so much energy and memory that they are actively choking their own hardware. To understand why this is happening, we have to look at the foundational engine of modern AI, the transformer. When you type a prompt into an LLM, it uses a mechanism called self-attention. To understand the 10th word in a sentence, it looks back at the previous 9. To understand the 100th word, it looks back at 99. To process a massive document, every single word must look at every other word. This creates what engineers call quadratic complexity. If you double the length of the text, the compute power required does not double. It quadruples. If you increase it tenfold, the cost explodes 100-fold. This is the attention tax, and every time you chat with an AI, a hidden ledger of data called the key value cache is ballooning in the background, hogging physical memory inside a graphics card that is running out of space. But the industry tried to bypass this math anyway. In late 2024 and 2025, companies marketed context windows of 1 million, then 2 million tokens. The public assumed this meant the AI could perfectly recall anything within that window. But they were wrong. Researchers testing these giant windows discovered a phenomenon known as the needle in a haystack problem. If you hide a specific piece of information in the exact middle of a long prompt, the model almost always misses it. It recalls the beginning, it recalls the end, but the middle becomes a cognitive blind spot. We did not build an AI with a photographic memory. We built an AI that frantically tries to hold open a 1,000-page book all at once, eventually dropping pages in the wind. Imagine you hire a lawyer to analyze a complex legal case. Every time you ask them a question, they insist on rereading every single page of the case file from scratch, laying thousands of documents across a giant floor. If the file grows to 10,000 pages, they need a bigger room, more tables, and hours just to glance at everything before they can give you a simple yes or no. That is the transformer. Now, imagine a different kind of lawyer. As they read each page, they update a single, highly dense summary notebook. They close the original files and keep only this distilled digest in their hand. No matter how many thousands of pages are added to the case, they only ever look at this one notebook to answer your questions. This is the fundamental difference between attention-based memory and recurrent memory. This shift from hoarding data to compressing it has triggered an architectural rebellion. Researchers have turned to state space models, or SSMs, with an architecture called Mamba leading the charge. Unlike transformers, Mamba does not keep a growing history of every word it has ever seen. Instead, it uses mathematical principles derived from classical control theory to continuously update a fixed-size internal state. As new words flow in, the model compresses them into this hidden state, forgetting the useless noise and keeping the vital signal. The computational complexity drops from quadratic to linear. Doubling the text now simply doubles the time, and the memory footprint remains entirely flat. It is a massive breakthrough in efficiency, but it comes with a devastating trade-off. Because Mamba compresses information into a fixed state, it cannot do what standard attention does so well: exact replication. If you ask a pure state-space model to copy a long sequence of random numbers or find a highly specific quote deep in its past, it struggles. The compression is lossy, much like a JPEG image. To solve this, AI labs are building hybrids. Instead of choosing between the file cabinet and the notebook, they are building systems that stack both. A hybrid model might use 90% state space blocks to process massive flows of text cheaply, and interleave 10% attention blocks to pin down crucial details. This hybrid approach is quietly becoming the standard for the next generation of open-weight models, proving that the future of AI is not a single architectural monopoly, but an elegant compromise. At the same time, we are realizing that memory does not have to live inside the weights of the neural network at all. The rise of advanced reasoning models highlights a different strategy: externalized cognitive memory. When these models face highly complex tasks, Like scanning software for critical vulnerabilities, they do not rely on their static attention windows. Instead, they output an explicit, step-by-step chain of thought, essentially talking to themselves in a digital scratchpad. They can write and execute code, save the results to an external file, and read those files back when needed. By moving memory outside the active neural network and into external environments, we can run incredibly deep, multi-step reasoning tasks without ever overloading the physical memory of the underlying silicon. The era of brute force scaling is ending, not because we ran out of data, but because we hit the physical limits of memory. The obsession with infinite context windows was a brute force approach to a problem that required elegance. By embracing recurrent architectures, hybrid systems, and externalized reasoning loops, computer scientists are aligning artificial intelligence with the laws of physics and biology. The human brain does not remember every pixel of every second of its existence. It compresses, distills, and retrieves on demand. As AI shifts from hoarding data to mastering compression, we are finally building systems that do not just store information, but truly understand what to keep and what to let go.